Okay. Any question from this time? I guess before start, as you might already know, we will have finals next week, and finals just like the midterms. Finals will be on next week Friday, and the range will be everything, but it should primarily it should have a big part in the Laplace transform and the transform, but obviously everything from previous part can be in the exam in maybe implicit or explicitly. Okay, that's the final. Okay, any question? And also a reminder there are class review going on, and so if you have time, you can go to do class review in that should be called class evaluation in 校务资讯系统. Yeah. Okay. Anyway, so let's go back to the class. So last time we go through the property of the ROC for the Z transform. So it's really like the property we have for the Laplace transform, except that the ROC now are rings instead of strips. So you kind of feel that you loop the ROC around. So you bend the ROC into a ring instead of the strip for the Laplace transform. And the imaginary axis, which was very important in Laplace transform, is now this unit circle. Okay, and so you have like the right-sided function has the ROC to the outside, and the left-sided function has the ROC to the inside. And now we have two special points, which is 0 and infinity, and etc. Okay, let's see, do we have more picture? Yeah. So there are three different kinds of housing. And obviously they're still bounded by poles for rational function, etc., etc. Okay, then that's the ROC. Then let's go to a different topic today. So it's inverse Laplace transform. We go through this, we gave an overview of this really quickly last time. And now let's see those carefully. So we say there are three ways to do inverse Z transform. So first one is you do integration, which we will derive, but once again we don't really know how to do counter integral, so we just leave with the form. And the second method is the partial fraction expansion, which is a little different now because we basically need to expand in 1 over z. Because we have less, a more complicated form of the partial fraction of our exponential decaying function. Then the method 3 is something unique for Z transform, that is because we know Z transform has a very special power series form, so if we can express our big X function in terms of a power series with maybe inverse power, then you can just read from the series coefficient what's your X of n, so your signal in time domain is. Okay. Why do we have? Okay. We shouldn't. Okay. Anyway. Let's start with method 1. Okay, so let's derive this Z transform, inverse Z transform counter integral. And as in Laplace transform, we want to use the correspondence to Fourier transform because we know how to do inverse Fourier transform. And we know Z transform is similar to Fourier transform in the ROC. So if we have big X in some contour in some Z equal to R e to the j omega, and if it is in ROC, then we know this is a Fourier transform of some function that depends on R. So let's say if it is R e to the j omega is some circle with fixed R, and so on some fixed circle, we know that the Z transform is just the Fourier transform of a very similar function to your x of n is your x of n times extra factor r to the minus n. So it's probably exponential decay or exponential growth depends on whether your r is bigger than 1 or smaller than 1. Okay. So you have this hy exponential term, and your z transform is just the Fourier transform of this function. And because this is a Fourier transform, then we know how to do inverse Fourier transform, so we can do inverse Fourier transform on both sides. Then obviously this side just get back to the x over n r to the minus n, and this other side it becomes the inverse Fourier transform of your big X e to the j omega. Okay. Remember that we need to be inside RC. Okay. And then we start to write down the inverse Fourier transform. Okay. So first we move this r to the n to the other side, because what we want to find is this x over n. So we keep everything else to the right hand side. So if x over n equal to r to the n f minus 1, this thing, and we have explicit expression for this f of minus 1. So it's this integral of everyone still remember. This is from the inverse Fourier transform of a discrete time function. So 1 over 2 pi and the integration over 2 pi of your omega. And this thing times h e to the j omega n. Okay, so this is the inverse Fourier transform. And then we can make this into even cleaner form. So you move this Rn inside, and you move this R inside here, then you combine it to this e to the j omega n, and you see that it's R times e to the j omega to the n. So this is z to the n, right? So it's pretty nice. So yeah, so this is a counter integral. It's kind of funny. Well, now it's expressed in terms of omega. So it's integration in terms of omega, but we kind of want to see this as a counter integral into z. Okay, and so let's change this omega value to z value. Okay, so we have this. Then we want to do change of variable from omega to z, and remember z equal to r e to the j omega. Okay, and we are taking r fixed to make everything easy. So yeah, because the star we have always been considered r fixed. So r fixed, then we do this infinitesimal calculation first. So we want to relate d omega with dz, and so dz. So you do this differentiation, do the differential of this part with respect to omega. So r is a constant, so you just have r, and differentiate z to j omega, get hrj downside, and then that's d omega. Okay, and then you can look at this and see this r e to j omega is still z, so it's just z omega. And but you want to express omega in terms of z, so you move everything to the other side, so you see d omega 1 over j z minus 1 dz. Okay, so luckily everything can be transformed nicely, so you can transform every omega into z without every r and omega left. So you see this is z to the n, and this is z, and d omega is this 1 over j z to the minus 1 dz. So you combine everything, then it's 1 over j to the outside, you have 1 over 2 pi j, and you have some integration, which is omega from 0 to 2 pi, but now it's z on a circle, so you write this circle. And as we said, x over z, and the z to the n, but you have h z to the minus 1, so z to the n minus 1 dz. Okay, so that's a derivation of the counter integral. And let's see, we don't have a picture, but yeah. So let's draw a picture. Picture. Where am I? Here. Okay. So the idea is say, let's see. Say for example, if your ROC is outside here, right? And then you have some R. Then you integrate this over some R. Like this, then your integral is something somewhere inside ROC, and so this is R, and so you want omega from 0 to 2 pi, so it's this circle. Okay, and so just like before, the contour doesn't really, the shape of contour doesn't matter. It can be deformed a little bit, as long as you are not closing any pores when you do the deformation. And but if you are inside ROC, that should be always true, because there is no pores inside ROC, so you can just have like a counterclockwise circle anywhere inside your ROC should be fine. Anyway, so that's the contour integral, which we won't actually tell you how to do, but it's pretty cool. And you can look up some complex analysis thing, and you will see that this thing will be equal to some value times you will just look at how many poles you actually inside this circle. So maybe there is a pole somewhere, there's a pole somewhere, and every pole will give you some value. But that's for complex analysis. And for now, we just tell you that this is a formula, and we can compare it to Laplace transform. You see that it's a little different. So those two are Z transform, and the lower two are Laplace transform. You see that the definition of Z transform is kind of like definition of Laplace transform. So you have Z prime e to the minus n corresponding to e to the minus st. But the inverse transform is a little bit different, because you have e to the st here, but you have z to the n minus 1 instead of z n e to the z to the n. I guess that's just something happened. And yeah, you can think about why is this minus 1. But it's something different when you do this contour ground circle. You get h minus 1 here. So you see this n and st, but it's n minus 1 and st. So that's a little different. But we won't actually tell you how to do the integration. Okay. I guess so. Any question for this very, I guess, qualitative description? Anyone interested in contour integral? It's not. Yeah. Okay. So that's a theoretical derivation, and let's see something that you probably won't see more in your homework, because you know how to calculate this. So this is a partial fraction expansion, as we always do. Okay, so for example, if your x over z look like this, so this 3 minus something or something times z minus 1, and then later part will refactor into 1 minus this 1 minus 1 over 4 z minus 1 times 1 minus 1 over 3 z minus 1, and with some ROC. And then you see that you can do partial fraction expansion into those two terms. And those are the terms we like, right? Because as an example, like 10.1, we have that 10.1 and 10.2. With that, if we have 1 over 1 minus a z minus 1, then we know that the inverse transform exponential decay in positive time or exponential decay in negative time, depending on where your ROC is on the outside of the pole or inside of the pole. Okay. And so that's basically what we do. But here is a little tricky, right? Because this form is more complicated than Laplace transform. Laplace transform, we just have 1 raised minus a. But here we have this z minus 1 here. So yeah, so when you do partial fraction expansion, you want to express in terms of polynomial of z minus 1. So you probably want to express your rational function in terms of z minus 1 instead of z before. So we can factor the lower part into this fraction, these roots to z minus 1, and yeah, and you can then partial fraction into fractions of z minus 1, because only those terms with z minus 1 we know how to do the inverse transform. Okay. Yeah, so that's actually a bit tricky part, but unfortunately we don't have example to see the detail of dealing with z minus 1. But we're going to see example of dealing with the different ROC. So different ROC is basically same as the Laplace transform. So we can go kind of quickly. So if you successfully decompose your Z transform, this big X of Z, into partial fraction, then okay, well, let's draw the poles of this example. So there is a 1/4, there is a 1/3. Okay, so 1/4 for this part, this pole, and 1/3 for this pole. And so you see the ROC can be 3 parts. And here we are taking the almost ROC. So the ROC will be outside of both of those poles. And then you see that the partial fraction, when you think about the ROC of those partial fraction, is outside of both of them, so both of them should take the outside one. And as we said, that correspond to the example 10.1, and that's the right-sided exponential decay. So then here this 1/4, you become this 1/3 to the n, and obviously you have u to the n, and this 1/3, then you have, where am I? Sorry, 1/3, then 1/3 to the n, and obviously it's linear, so 2 goes to 2, and so you just have a linear combination of this 1/4 to the n and 1/3 to the n, and times u to the n. Okay, and yeah. It can be a little bit tricky in terms of writing partial fraction into this. I think the tricky here is, remember, you are expressing in terms of polynomial of z minus 1. So you can have those partial fraction of z minus 1. Okay? So hopefully you can deal with the partial fraction expansion. And let's look at the ROC. But it's very similar to Laplace transform. So as we say, there are 3 possible ROC. And so this is almost ROC, and obviously we are going to see the other 2. So if you are picking the middle ROC, so your ROC is between 1/4 and 1/3, then you will be outside of the 1/4 pole, but inside of the 1/3 pole. So for the ROC of the 1/4, you take the outside one, and for ROC of the 1/3 pole, you take the inside one. Then obviously you just get 10.1 for this, and you use example 10.1 for this, and example 10.2 for this. And here is the reminder for example 10.2. Your x of n is this minus a to the n, and u of minus n minus 1. And yeah, so a is still this 1/3, so it is minus and 1/3 to the n, and 2 from these 2, and u of minus n minus 1. And yeah, so you add them together, it's become your x of n. Yeah. And finally, we take the innermost ROC. Then both of the ROC is on the inner side, so you just get the left-sided function. So both of those two terms have this u of minus n minus 1. Okay. And yeah, so those are the easy examples. This is an easier example because we have no multiple poles on the denominator, right? So here are all linear terms. So we see that if you can decompose your terms all into this first order term, y minus ai z minus 1, and the linear combination, then obviously you just need to look at 10.1 and 10.2. So you just look at ROC, is it outside or inside of each AI? If it's outside, ROC is outside of the AI, then you take 10.1 and you get this right-sided exponential decay, and if it's inside, then you take 10.2, then it's this left-sided exponential decay. It's a to the ai to the n times u minus n minus 1. And obviously, if you have higher order, then we need to use the differentiation property again to derive the inverse Fourier transform of higher order of this, which we'll not see here right now, but you can probably imagine how that goes. Okay, so that's the most practical inverse Laplace transform you can do. This is for rational functions. So any question? This? No? Okay. schedule to be very quick today. Okay, then method 3. Method 3 is kind of funny. It is something that we don't have a counterpart in Laplace transform. We can do it here because you just stare at this thing. So this definition of big X of Z is summation from minus infinity to plus infinity x of n z to the minus n. But if you are familiar with calculus or just good analysis, then you think this side you can interpret it as the power series expansion of z, right? This is just power of z with different number of power, with power from minus infinity to plus infinity. So this is like a power series expansion of z to n, right? So say if you are n from 0 to infinity, then that's a Taylor expansion you should already see in calculus class, but hopefully you remember. But here this is a bigger expansion than Taylor series expansion. This is the expansion from power from minus infinity to plus infinity. Okay, so this is series expansion in terms of z, and then you think that if you can write your x of z in terms of your series expansion, then you can just, in terms of a series expansion in terms of z to the minus n, then you can just read the x of n from the coefficients. Okay, so let's see 3 examples of how this works. So this is actually not as systematic as method 2 because because we are kind of bad at analysis here, and we don't tell you a very systematic way to how to write everything in terms of this series expansion. But we will see some special example. Okay, so first special example is, if the quadrant just give you the series expansion. Okay, so your x of z is just given in a series expansion form. Then obviously you can read the coefficient just from whatever is given you. So x of z is 4z to the 2 and plus 2 plus 3z to the minus 1. Then you see that this is a sum of 3 terms here, right? So it's n equal to minus 2 with x of minus 2 equal to 4, and n equal to 0 correspond to this term, and n equal to 1 correspond to this term, right? And it's all 0 everywhere. And then you can just read your x of n from those 3 coefficients. So you see that your x of n is, if you just compare this to this, you see that your x of n has n equal to minus 4, it has value 4, and at n equal to 0, because there is no z, then it is 2, and at n equal to 1 is 3, right? And it's 0 otherwise, because you have no other term. Okay, so so this is the idea. If your x of z is written as a series expansion, power series expansion in terms of z, then you can just read from the coefficients to those z powers, and those correspond to your x of n. Okay, so that's very nice. And we can write this a bit more compact by remember that we can think x of n as sum of different spikes at different time. So this 4 at n minus 2 we can write as 4 times the delta function of n plus 1. So this only take value 1 at n minus 2. And similarly 2 times delta of n and 3 times delta of n minus 1. Remember, this is what we do in chapter 2. So just write x of n as its values times the delta functions. Okay. And then something nice is from those two, or maybe a little bit from just this. You see that there is a nice Laplace transform pair, that is Laplace transform pair. So not Laplace transform, Z transform pair. So if you have delta n plus n0, you see that it Z transform to Z to n0. You can just read it from here, right? So this delta of n, or just see this like this delta of n plus 2, Z transform to Z squared, etc. Okay. And yeah, so you can think about those just reading is using this transform pair. Okay. Okay. Any question so far? Okay. And then let's see a little more example of this. Although this is not very generic, but you can kind of see this idea goes a little further than just given this. So we'll do something that we already know the answer. So this example, this corresponds to the example 10.1, right? So our favorite function again, big X of z equal to 1 over 1 minus a z minus 1. And there are two possible ROC. First we do the outside one. So ROC is z bigger than a. And okay, so this doesn't look quite like a power series, but we can expand it into power series by doing long division. So it kind of feel like, so the long division is the middle part, right? So we are dividing 1 with 1 minus a z minus 1, and the matrix is 1 with 1 then. So you subtract 1 from 1 minus, sorry, you subtract 1 minus a minus 1 from 1, then you get extra a minus az minus 1. So you get this az minus 1 left over. Then you should plus az minus 1, and then you will get a squared z minus 2 left over, etc. And the other way, if you see this in inline algebra, then you see this means 1 equal to 1 times 1 minus az minus 1, and with extra az minus 1 left over, then this az minus 1 will divide with 1 az minus 1 again, then you get a squared z minus 2, and then you divide it again, you get a cube z minus 3 cube, etc. So like this. And yeah, so we can kind of write this regional function into a power series expansion in terms of z. So it's 1, and you can guess the formula here already. So it's 1 plus az minus 1, a squared z minus 2, so it should be a cube z minus 3, etc. And then important thing here is now we need to use ROC. So this expansion converge only when absolute value z is minus bigger than absolute value of a. So all the terms are getting smaller and smaller because az minus 1 absolute value is less than 1. And this is the power series expansion. Yeah, is the geometry series with absolute value less than 1. Okay. And yeah, so this is converging, and so this is a valid expansion. And then we once again look back to our power series expansion. Then we see that here we have this n equals 0 term and all the positive n term. Okay. And for negative n term means positive power of z, there are just no terms. So for n less than 0, x over n should be 0, and x0 should be this 1, and x1 should be this a, and x2 should be this a squared, etc. And then yeah, then you add it back, then you see that your x of n is actually our familiar a to the n u of n, because yeah, because at 0 is 1 and at 1 is a, and as your n gets larger and larger, you get this exponential decay in terms of a. Okay, so yeah, you get this exponential function in terms of a. So you see the yeah, by doing the power series expansion, we get the same result as our 10.1, and so this makes sense. Okay, and let's see an example that you probably guess what we will do. So yeah. So we talk about 10.1, and we're going to talk about 10.2. So if our ROC is on the other side, so if our z is less than a, then our az minus 1 is bigger than 1. And then this series won't converge. Okay? or this series, because those are getting bigger and bigger. So that's the wrong answer, and that should be because we know the inversely transform should be the other function. And yeah, so we take converging the division, long division now. So when we do this minus az minus 1 plus 1, we do the division the other way. We're matching this az minus 1 term first. Then if you do this like the other side division, then you will get the series like minus a minus 1z minus a minus 2z squared, etc. Now you see we get the positive powers of z here now. Okay, because we are matching the other side. So we are matching this az minus 1 first to whatever remainder you have. Okay, and yeah. So now everything will be powers of z a minus 1 instead of a z minus 1. Okay, and yeah, so now this will be converging because now it's in positive powers of z a minus 1, and I would say, well, z a minus 1 is less than 1. Okay, and then now you once again compare this to this expansion. Then you see that now we only have negative terms, and the terms are minus a to the yeah, minus a to the n. Okay, and it's starting minus 1 to minus infinity, so you have this u of minus n minus 1. Okay, and yeah, so that's consistent with our 10.2. Okay. So the power series expansion works a lot of time. And as another example, let's try the Taylor series expansion. So Taylor series expansion, here is a quick reminder of calculus. It says that any function, actually probably when you do calculus, your z is probably real, but actually it can work for complexity also. So just save that this works. And yeah, so for your analytic function x of z, big X of z, you can expand it around any z0. So you can write as x of z0, which is value at 0, then those summation of powers. So you will take the distance between z and z0. This is actually a complex number, and then you have here is probably the important part, so that's this. Right? Okay, and you will take the nth derivative of your function with respect to z, and yeah. So it's n here and n here, and yeah. So you have those higher powers of difference between your point you are taking value and this reference point 0. Okay. So you are expanding this function in terms of powers of z minus z0, and the coefficient will basically proportional to nth derivative of your function, and also normalized by this n factorial. And the easier way to see this is you can just choose z0 equals 0. Then you just get power of z here, right? But okay, but a little complaining is that so here we have this n from minus infinity to plus infinity. But if you just do this, then you just have n from 0 to plus infinity. So it won't match everything. But anyway, we can do this for some example, and which will actually give us a negative power. Kind of funny. And yeah, so our example is this x of z is now something very weird. It's not rational at all. Log of a 1 plus a z minus 1. Okay, and I believe this thing has a pole at a also because log of 0 is a pole. Anyway, and we are taking the LCO being outside a. Okay. And yeah, and because z is bigger than a, then we can kind of expand with powers of this az minus 1. Yeah. And okay, so what we are doing is we use Taylor series expansion to expand this function log of 1 minus v. So think about, so basically this is just making notation easier. So we think about az minus 1 is something called v, and v has an absolute value of less than 1. So this is something small enough, so it's probably easier to expand it down it. Okay, and anyway, log of 1 minus v, then we can do Taylor series expansion with respect to v. Then it will be this thing. So as we say, it will be power of v, positive power of v, from 1 to plus infinity, because at v equal to 0, this is log 1 equal to 0. Okay, and so we have power of v, and if you do calculus, so here are some calculus that you can check. Skip that. So calculus is actually says that it's minus 1 to the n minus 1 and over n. So basically this will give you like a minus 1 factorial. So we'll cancel out to just level with n here. Okay, and this work when v is less than 1. And okay, so this is the power of v, and if you plug this back to this az minus 1, then so the positive power of v back to negative power of z. So it's a to the n, z to the minus n. Okay. And here let's skip all the calculus. Okay, so hopefully you remember the calculus. Basically the hardest part is remember d log x dx equal to 1 over x. Then after that, so this is the first derivative is just 1 over x. Then all the higher order one is the derivative of this. So this is power of x, and you should remember how that goes. Okay. And yeah, let's see. Yeah, so we are using this equation with, well, not actually on x of z, but we are on x of v, and we are taking v0 as 0. We are expanding around v equal to 0. Okay, and anyway, so that's our expansion. And we got x over z as this power series of z. And as we said, then once again, this is a power series of z with some negative power. Then we can just look at the coefficient and see that x over n is minus 1 to the n minus 1, and this is a to the n over n, and only when n is bigger than 1 and 0 or otherwise. So if you write this bracket in a more complex form with this u, then it's minus a to the n over n and u of n minus 1. So this u of minus 1, make sure that you only take n bigger equal to 1. Okay? Any question? Yeah, so that's the power series method for inverse Lie transform. I feel this is probably not too practical, but if it gives you a nice intuition about the transform. You know that the transform kind of just make your x over n into a power series of z. So if you get a power series of z, then you can inverse transform back to x over n really quickly by looking at the coefficients. Okay, so yeah, it's a good thing to remember is this: z to the n go to z to the n0 go inverse transform back to delta of n plus n0. Okay, yeah, so that's the ways of doing the transform, and I think we can actually go very quickly through this geometric interpretation because it's not too different from before, and it's very qualitative. So let's just go through this quickly. So yeah, let's see some geometric interpretation of the Fourier transform from the pole zero plot. So it's basically just like a Laplace transform. We'll write the pole zero plot, and we remember the Fourier transform is a Z transform on this unit circle. So we just think about this unit circle. So this unit circle corresponds to omega from 0 to 2 pi, and so we just go around this circle and look at our h of z and think about how h of z should change when you are going around this unit circle. So for example, we start with our first order system, which is this system. So first order different system, y of n turns and y of n minus 1 turn, etc. And let's give all the solution. And yeah, anyway, you can do probably Fourier transform to get the solution, and that's frequency response. And if you write this frequency response in terms of z, so e to j omega equal to z, so then you get back to this 1 over 1 minus a z minus 1. And you write it in terms of rational, so it's z over z minus a. So it's 0, it's z equal to 0, and the pole is z equal to a. Okay, and then let's suppose a has absolute value less than 1. Then, yeah. So pole at z equal to a, 0 at z equal to 0. And suppose a is less than 1. Then the pole 0 plot look like this. So you have a pole at a and a 0 at 0. And you think about your Fourier transform is working on the unit circle with omega from 0 to 2 pi, 0 to 2 pi. It's periodic. And then, yeah. Oh, why is this so ugly? Anyway, so that's h of z. I see. So let's do this from now. So for now, h of z, h of z is this. And okay, so the distance to 0 never change. So you are basically just looking at the distance to pole. And obviously the distance to pole is lowest when you are here and highest around here. So the magnitude should be highest when you are at omega 0 and go to lower when you are to pi, then go back where pi back to 2 pi, etc. And also you can analyze the angle. Okay. The angle, yeah. The angle we don't do analysis, but you see that there is also something changing very fast around this 0. And here we have two things. So you see that if your pole is getting closer to 1, then obviously the change should be higher and higher because you have this z minus a. So if your a is closer to your circle, then obviously this z minus a should have higher change around omega equals 0, and also your angle will change faster around omega equal to 0. Okay, and oh, we are going super fast. Okay, anyway, we can finish this in 10 minutes. And that's first order system, and that's the second order system. So here's a very quick view of the second order system equation. So y and y minus 1 and minus 2. So this is first order, second order. And the coefficients written in some way for some reason. But anyway, it has, you can Fourier transform, so for the big H. And it has, you can then decompose this into two poles. And if you solve the poles, it will be r e to the j theta and r e to the minus j theta. Okay, and r and theta are here. So this is the r and there is theta. Okay, and so yeah, so those two poles. And also because those are once again this is z minus 2 thing. So if you write in function of z, so there is actually z squared on the top. So 2 zeros is z equals 0, but once again z at 0 doesn't do much. And so pole 0 plot look at this. You have double 0 at 0 and pole at r e to the j theta and another pole at r e to the minus j theta. So those two poles. And also you can think about when you walk around walk around a circle, and Then when you are getting closer to this pole here, then your is we don't have a nice equation. Anyway, so you work close to this pole, then that z minus a1 term will get z minus z1 term will get small, and 1 over z minus z1 will get large. So you get a peak here, and then you go away, then you go down, then when you walk around here, then you get the second peak. And obviously, if your r is closer to 1, then those poles are closer to your circle, then the peak will get larger. And yeah. And also you can count the angle, and you will get 2 large change once again around this theta and minus theta, and other places they also have change. You can do the calculation from the geometry. Oh, okay, we are faster than we already expected. But yeah, so that's a geometric interpretation. And any question? 4 minutes. So let's just have a 1 minute overview, and next time we'll talk about property of the transform. There are lots of property, and they are kind of similar to the Laplace transform, where you need to take care of the ROC again. So the ROC will be this kind of thing. You have intersection, but you can cancel poles, so your ROC can be bigger than those. So your ROC will be containing some intersection, etc. And also the property will be kind of like the discrete time Fourier transform, and go to when you change e to j omega to z. Okay. So yeah, that's it for today. Once again, we see this geometric interpretation of Fourier transform, where you look at the bigger thing, you look at the point 0 in the z-plane, then you think about Fourier transform is on the unit circle, then you kind of get the property of the big H function through different omega by just walking through this circle. And also we have to do the inverse Z transform. We'll go to 3 methods. The last one is you try to make your x of z into a power series, then just read the coefficient back to your x of n. And the second one is the usual calculation you will do probably in your homework and the exam, that you do partial fraction expansion back into form of 10.1 or 10.2, but the form now is a little ugly. You need to expansion in terms of z minus 1. Okay, and you do fraction expansion, and if it's linear, you can use 10.1, 10.2. If it's not linear, you probably look up another table that we'll derive later. And finally, there is method 1, which is most general, but we don't actually know the full calculation, which is you get a counter integral inside LOC. It is a really cool mathematical form. X of n is 1 over 2 pi j, and the counterclockwise integral inside LOC, and your x of z times z to n minus 1 then dz. Okay? Any question? There is no question, then I think we can stop a little early today. And yeah, on Friday we should finish this chapter by skipping some parts. Okay, so see you on Friday.